Hi, my name is BINTI ARIFFIN, and this is Group 6 presentation for Practical 3. So before we get started, this is the list of group members for Group 6 according to the order of the presentation. So for the question 1, show the neighboring joining tree and the major clades, lineage, and also groupings. So as you can see here, we have our root neighbor joining tree. We have three groups, which is the first one is the Malawi group, the second and third is the Tanganyika. So these are the species for the groupings that I said before. We have the Pseudochromis, Citrocara, Rhampochromis, Pseudotropius, Melanochromis, and also Petrotilapia. For Lake Tanganyika, we have Tropius poli and also Petrochromis. For Lake Tanganyika Group 2, we have Labochitulis, Cytotilapia, Julidochromis, and also Betty Bates SP. I will be passing the presentation to my group member. Thank you.
Our key focus will be on bootstrap values, which are critical statistical measures indicating the reliability of each branch on our evolutionary tree. So, what are bootstrap values? In simple terms, bootstrap values ranging from 0 to 100 represent the percentage of times a specific grouping or clade appeared when repeatedly resampled our genetic data. A value above 70 generally suggests good support, while anything over 95% signifies very strong statistical confidence. So, our results, the bootstrap values explain the Lake Malawi group strong monophyly 98% support. Let's start with the Lake Malawi group. This large clade encompassing Placidochromis, Critocara, and others 98 bootstrap value show 98 bootstrap value. This is excellent support indicating a strong definitive relationship among these species, suggesting they all share recent common ancestor and have undergone a significant adaptive radiation. The internal Lake Malawi relationship, which are Critocara and Rhampochromis, definitive relationship is 100% support. Within Lake Malawi, the pairing of Cytocara and Rhampochromis stands out with a perfect 100% bootstrap support. This means this specific relationship appeared in every single analysis, offering definitive confidence in their close evolutionary tie. And about Pseudotrophius and Melanchromis, Imbuna sister group 99% support. Next, we have Pseudotyphorus and Melanochromis are also very strongly supported as sister species with 99% bootstrap support. This aligns well with their biological classification as rock-dwelling Mbuna cichlids, reinforcing their close evolutionary proximity. Melanchromis, however, we observe a much lower 45% bootstrap support for the relationship between Melanochromis and Petrotilapia. This indicates a weak and uncertain relationship, suggesting that this particular grouping is not consistently recovered across our analysis and warrants further investigation. And moving to late Tanganyika clade, the grouping of Tropheus poly and Petrochromis shows 75% bootstrap support. This is considered a good, well supported grouping, though not as overwhelmingly strong as some of as Lake Malawi relationships. The placement of Lobokilotus on the tree has 69 bootstrap support. while just shy of the common 70% good support threshold. It suggests moderate confidence in its position, indicating an acceptable level of certainty. Finally, the deepest split in our tree, representing the root split with Pathibatis sp as an outgroup, has 52% bootstrap support. This lower value is not uncommon for every ancient divergences. It points to a low level of support and highlights the inherent uncertainty in resolving relationships that occurred much further back in evolutionary time. Biological interpretation In the biological interpretation, what do these numbers tell us? The high bootstrap values in Lake Malawi underscore its recent and rapid adaptive radiation. In contrast, the more varied and sometimes lower support in Lake Tanganyika clades reflect older and more complex evolutionary history of this ancient lake. Essentially, the further back in time, the more challenging it becomes to definitely resolve evolutionary relationships. Thank you.
For the third question, what is the most basal species of the Malawi clade? It is actually the earliest Darwinian lineage in the group. On the tree, it is the species that branches off first from the common ancestors of the clade. So how we identify it? We first look at the Malawi clade in the NG tree and find the first branch within the group. The species on the branch is the most basal. So within this group, the species AY911829.1, the Blymphocrimis branches off first from the other Malawi species. So this makes it the most basal member of the Malawi clade.
Okay, question number 4 is based on the tree, which species are most related and what is the range of genetic distance between them? Okay, the most closely related species in the tree are clearly Pseudotropius and Melanochromis, as indicated by their extremely short branch length and perfect bootstrap value at 100%. And another closely related pair is Placidochromis and Cytochara, which also have a short genetic distance and a high support value of 99%. The genetic distance between species can be estimated using the scale bar provided at the bottom of the tree, which represents 0.02 substitutions per site. Closely related species like Pseudotropius and Melanochromis have a genetic distance of around 0.002 until to 0.005, while more distantly related species such as Betty bats and the Malawi show distance up to 0.04 or higher, indicating greater divergence. That's all for question 4. Thank you.
Hello, my name is Hazim, and I will be answering question 5, which is, are these species related based on their morphological similarities or by locations? So, based on the phylogenetic tree results, these fishes are primarily related by locations than morphological similarities. We have few evidence here, and the first evidence is that the Lake Malawi species actually form a monophyletic group, meaning that these species are descended from a common evolutionary ancestor. In the all of the species in Lake Malawi, they cluster together regardless of their morphology. The second evidence that I would like to present is that morphological similarities do not predict phylogeny. Even though they are morphologically, they seem similar, but the molecular phylogenetic analysis reveals otherwise. And then the third evidence I would like to present is that this is actually an interesting examples of convergent evolution, where the convergent evolution is the process where unrelated species independently evolve similar trait as a result of adapting to similar environments. So in this case, we have the similar morphologies of these two different species of lakes that have evolved independently in each lake to fit the same ecological niches. I would like to draw our conclusion here. So we have concluded that the phylogenetic relationships are determined by geographic origins and evolutionary history, and not solely by morphological similarities. And this is actually convergent evolutions that these species evolve in the same way to fill the same ecological niches. That is all from us, Group 6. Thank you so much for listening.